Hello everyone. So I'm back with another video, and today we are going to discuss the reaction and the mechanism behind Reimer Tiemann reaction. So this is a very important reaction which is undergone by phenol. So let's dive into the reaction and understand the mechanism behind it and also the products obtained. So this is a reaction when phenol is treated with chloroform CHCl3 and a base, that is NaOH, at a very specific temperature, 60 degrees Celsius. Okay, and there are two major products over here. The first product is this. So here we have a benzene ring with an OH group and a CHO group, an aldehyde group. So since aldehyde is the more important group over here, so we will start naming with respect to this aldehyde group. And this hydroxy group or this OH group is at ortho position to this aldehyde group, that is ortho meta para, again ortho meta para. So this is the ortho position. So with respect to this CHO group, this OH is at the ortho position. Alright. So the name of this compound is orthohydroxybenzaldehyde, because this part is benzaldehyde, and at the ortho position of this compound is the OH group, and when OH is used as a substituent we use the term hydroxy. So orthohydroxybenzaldehyde, and the common name for this compound is salicyl aldehyde. So the common name is salicyl aldehyde. Okay, and there is another product. The only difference is that the hydroxy group here is at the para position. So this is para hydroxy benzaldehyde. Para hydroxy benzaldehyde. Okay. So now which of these two is a major product? So for that we need to look at hydrogen bonding. Here the hydrogen bonding will have a more dominating effect over steric hindrance. So if we see that so if we observe steric hindrance, so then this compound obviously has more repulsion between the OH and the CHO groups, because there is more repulsion between them, so there is more steric hindrance, where here the steric hindrance is comparatively lesser. But in this case, the hydrogen bonding factor will dominate over the steric hindrance factor, and so we can observe that this hydrogen, it is bonded to oxygen, so it is capable of forming hydrogen bonds, and we have an oxygen over here. So this hydrogen and this oxygen, they will form a hydrogen bond, an intramolecular hydrogen bond, because it is within the same compound, and as a result of that, the stability of this particular salicylaldehyde compound will increase, and so this will be the major product. Let me show you the hydrogen bonding in salicylaldehyde. This is the benzene ring, this is the OH group, this is the aldehyde group. So this hydrogen has a considerably delta positive charge because it is bonded to electronegative oxygen, and this oxygen also has a delta negative charge. So there will be a force of attraction between this oxygen and this hydrogen, and so a hydrogen bond will be formed, and so a 1 2 3 4 5 6 membered ring will be formed over here. Okay, and due to the stability of 6 membered rings, this total compound will have high stability. Okay, because of hydrogen bonds to form a 6 membered ring. So this compound salicylaldehyde is the major product over here, and parahydroxybenzaldehyde is a minor product. Why? Due to hydrogen bonds. And what type of hydrogen bonds? Intramolecular. Because the hydrogen bonds are formed within the same compound. So it's an intramolecular hydrogen bond. So another important question is that why is this specific temperature, that is 60 degrees Celsius, is used in this case? So for that we need to know about the mechanism of the reaction. Then only we can answer that question. So let's get started and let's understand the mechanism of the reaction. So the first thing we notice is that there is phenol and there is a base. So NaOH is a base and we have phenol, and phenol is definitely acidic. So phenol will react with this NaOH to form phenoxide ion. Okay, so this OH minus from the sodium hydroxide will abstract the acetic hydrogen of phenol to form phenoxide ion. Let's see. So this is phenol, the OH minus, it will take up the H plus to form water, and we will get this compound, that is phenoxide. This is phenoxide. This is the conjugate base of phenol. Now this phenoxide can resonate. Negative charge will come over here. This bond will move over here and we get a resonating structure that looks something like this. So the negative charges come, so a double bond will be over here, right? And a negative charge will be over here and two double bonds. So this is the first resonating structure, and this is the resonating structure that will react in this reaction, not this one. Okay, this is the one that will react. Another important thing is chloroform CHCl3, whenever reacted with a base, yields a very good intermediate, that is a carbene. So what will happen is that this OH minus, okay, from the base, it will cause one of the Cl's to disappear from here, and by abstracting the H. This OH minus will abstract the H over here. As a result of that, there will be a negative charge on the carbon, and since there are three Cl atoms attached to a negative charged carbon, so there will be great repulsion between these charges and these atoms. So as a result of that, one Cl will move out and we will get an intermediate like this. This has two Cl atoms and it has two orbitals over here, and one of the orbitals has a pair of electrons whereas the other orbital is vacant. So this compound is called a singlet carbene. Singlet carbene. Why is it called a singlet carbene? Because the lone pair of the electrons is in one orbital only and the second orbital is vacant in this case. So that is why it is called a singlet carbene, because the lone pair is in a single orbital, not in both the orbitals. Okay. So in this reaction, this singlet carbene will act as a electrophile. Electrophile. Okay. This singlet carbene will act as a electrophile. Why? Because it has a pair of electrons as well as a vacant orbital. So the vacant orbital part will act as the electrophilic part, because this will be attracted towards electron rich part, because there are no electrons in it. So it will try to take up electrons. Okay. So this is why it will be acting as an electrophile. Okay. Now we have two of the major reactants. First is this and then this. So both of these will react to form the product. How is that happening? Let's see. So this is the benzene ring which we had drawn. Negative charges over here, the two double bonds. Now there is a negative charge over here and there is a vacant orbital over here. So this negative charge will be donated towards this vacant orbital, right? And so we will get this a carbon over here, because the negative charge has been donated. So it has formed a bond with this carbon, and two chlorine atoms. Now this compound, this is not aromatic, right? This is not aromatic because it is not obeying Huckel's rule of aromaticity. This carbon here is sp3 hybridized, whereas Huckel's rule of aromaticity states that all the carbons should be sp2 hybridized. So this carbon is sp3 hybridized, that is why it has lost its aromaticity. Now we all know that aromaticity is one of the highest degrees of stability that can be offered by a compound. So it will try to regain its aromaticity after this reaction. So what will happen is there is a hydrogen over here, because this carbon It is bonded to one carbon, one hydrogen, and two carbons over here. So there's one hydrogen over here. So what will happen is that this bond will open up, this hydrogen will move out, and this carbon will come over here. This bond will come over here. Okay? This hydrogen will move out and it will be transferred to this carbon because this carbon has a negative charge. Why does this carbon have a negative charge? Because of the presence of this lone pair of electrons. So it has a negative charge over here. So this hydrogen will move on to the carbon to satisfy the negative charge, and this part will regain the aromaticity. So this step, this is known as rearomatization. Why is that so? Because first it was aromatic. This phenoxide was aromatic. Then one of its resonating structures lost the aromaticity. Okay? And now again it is rearomatizing, which means it is again forming an aromatic compound like it was before. So because of that, this step is known as rearomatization. Okay? So now what is going to happen after all this rearrangement? So obviously this bond has moved over here. So oxygen has a negative charge. This bond has broken. So here we have drawn a single bond over here. Now this bond has come over here. Okay, let's see. This bond has come over here. So there will be a double bond over here. Two more double bonds. And now this hydrogen has come to this carbon. So this is the carbon. It has a hydrogen and obviously two chlorines. So obviously has two chlorines. Okay. Now, the last important step of this reaction is this is the compound that we got, but there is NaOH in the medium, right? There is NaOH in the medium. I had shown you there is NaOH. So this OH minus will now act as a nucleophile. So first in this step, it acted as a base because it has abstracted the acidic hydrogen. It has abstracted the acidic hydrogen, which is the purpose of a base. So this OH minus in this step, it has acted as a base. Now there is no point of it being a base because there is no acidic hydrogen to be abstracted. This hydrogen bonded to carbon is not electropositive, so there is no point in abstracting this hydrogen. So now this OH minus will behave as a nucleophile. So in this particular reaction, it is very interesting because this OH minus plays a dual role. It acts as a base as well as a nucleophile. First it acts as a base, then it acts as a nucleophile. So this OH minus, actually two OH minus, they will attack this carbon over here. Okay, another OH minus will attack the carbon over here, and these two chlorine molecules will move out. The two OH minus will replace the two chlorine atoms over here. So this is H, this is OH, this is OH. Now this is a geminal diol because two hydroxyl groups are attached to the same carbon, such as geminal diol, and two such electronegative groups like oxygen, when attached to a single carbon atom, cause great repulsion in it. So a stable product, that is water, will be formed. That is, we have to take out water because of the excessive repulsion over here. The water, if the water molecule leaves, then water is a thermodynamically feasible product. The delta H value is quite nice, and so the delta G value is supposed to be spontaneous. It is supposed to be negative for water. So if the water molecule will move out, then the repulsion will decrease and it will be able to form a stable compound. So here we are writing minus H2O because the water has been removed from these two OH groups, and the final product that we get is, so this has moved. So now this will be like this. It will form a double bond over here. Okay, because this hydrogen has been taken, so this oxygen will come over here, and so this aldehyde group is produced. Now if we hydrolyze it, then only it will form our desired product, that is salicylaldehyde. That is, we need to hydrolyze it over here. We need to add H plus over here. Otherwise, this product won't be formed. Otherwise, it will remain as sodium phenoxide form, right? Because in the presence of a base, this this O minus will exist as electrostatic forces of attractions with Na plus, not with OH. Only if we hydrolyze it, then only it will get converted into OH group. So this is the final products. So the entire mechanism we have followed and we have come to this product which matches with the product that we desired. Okay. So again, if I provide you a recap, so this OH minus acted as a base. It abstracted the acidic hydrogen of phenol to form phenoxide. The phenoxide resonated to form this resonated structure, which will react in this particular reaction. Simultaneously, this chloroform molecule reacted with this base to form a singlet carbene. Okay, and this singlet carbene had a vacant orbital as well as a lone pair of electrons. Okay, and this particular structure, it had a negative charge. So this negative charge attacked this vacant orbital to form this structure. Now this carbon had a negative charge, and this particular thing, it was not, this particular compound, it was not aromatic, so it wanted to be re-aromatized into an aromatic compound. So the hydrogen moved, this bond came over here, this oxygen carbon pi bond opened. Okay, and this hydrogen came to this negative charge of carbon to satisfy it, because the negative charge on a carbon atom is quite unstable, because carbon is a considerably electropositive atom. So a negative charge on this electropositive atom will be quite unstable. So the hydrogen satisfied this negative charge. Now this OH minus acted as a nucleophile. Previously it acted as a base over here. Now it has acted as a nucleophile over here. It replaced the two chlorine atoms to form a geminal diol. Now, since this was unstable, the water molecule was removed from here and it formed salicylaldehyde. Okay, salicylaldehyde was formed. The name of this compound, again I am mentioning, that is very important, the common name salicylaldehyde. So this I have done from the ortho position. You can do it from the para position also, and you will get this para-hydroxybenzaldehyde, the minor product. This is the major product. Now coming to the question which I had asked, that why is this 60 degrees Celsius temperature needed? Why is this needed? The answer is that at higher temperatures, this singlet carbene has a tendency of getting converted into a triplet carbene. That is, this is a singlet carbene, lone pair over here. At higher temperature, if I heat it, it has a tendency to get converted into this structure. That is a triplet carbene. So this is a triplet carbene. And this is a singlet carbene. At higher temperature, singlet carbene is converted into triplet carbene. So this triplet carbene does not have a vacant orbital, so it cannot act as an electrophile. It cannot participate in Reimer Tiemann reaction because the two electrons are distributed in the orbitals. There is no space for an incoming negative charge to be stored. It has no vacant orbital. Only one electron can be stored, but the negative charge always has two electrons. So whenever it is donated over here, it won't be able to fit in either of these two orbitals. So this triplet carbene, it won't be able to give Reimer-Tiemann reaction, and only singlet carbene can give. So if we maintain the temperature at 60 degrees Celsius, then the singlet carbene won't convert into the triplet carbene, and we will be able to obtain the successful product, salicylaldehyde. Okay. Yes, and another important thing is, unless we provide this H plus, it will exist in the phenoxide state. Okay. Now there is another Reimer-Tiemann reaction. Okay, this was the basic thing, and there is another Reimer-Tiemann reaction in which we use carbon tetrachloride instead of chloroform, and the product is also different. So let's see what happens if we use carbon tetrachloride instead of chloroform. So again we know that this phenol, we are using NaOH also, the same reactants, except Instead of CHCl3, we are not using CHCl3, we are using CCl4 instead of CHCl3. Okay, now let's see what will be the difference. So again, the OH minus will take up the acidic hydrogen, right? And we will get this phenoxide ion again. Now it will again form this resonating structure of phenoxide. This will react. Now carbon tetrachloride, the interesting thing is that this is the structure of carbon tetrachloride, right? Four Cl atoms bonded to this carbon. Okay. Now this negative charge will be donated to this carbon, and one Cl will move out because the carbon has to be tetravalent. Okay, if this negative charge is donated to this carbon, then one Cl will have to move out, because otherwise carbon will become pentavalent if all the Cl's are attached. So one Cl will move out, and so that the carbon remains tetravalent. So what we get is this 3Cl. 3Cl atoms are attached to this carbon. In this case, only 2Cl atoms were attached to the carbon. In this case, 3Cl atoms are attached to the carbon. So let's see what the difference is. So again, there is a hydrogen over here. So this hydrogen will move out. This bond will move over here. Again, this will open up. Again, there will be rearomatization to form this. Now in this case, we will require 3 OH minus, and again these 3 OH minus atoms will replace these 3 Cl atoms to give this. OH, OH, OH. 3 OH atoms are attached to this carbon. Okay. Now again there will be repulsion over here, so again a molecule of water will be taken out. So if I write minus H2 over here, so again one molecule of water is taken out, and I'm showing it on the next page. So again, if one molecule of water is taken out, then what will be the final product? How is this possible? See, I have taken out H2O from these three hydroxyl groups. So double bond will come over here, and there is an OH group attached. So there will be the formation of a carboxylic acid group over here, and that is the difference. Now, another important thing is that here we do not need to hydrolyze it further to form OH from this O minus part. Why is that so? As you remember, this hydrogen, this was removed during rearomatization. Okay, so we got an H plus from here. Now in this case, what happened? This H plus, it went to satisfy the negative charge on this carbon, so this was lost. This could not be used for satisfying the negative charge on this oxygen, because this had gone to this particular carbon, right? But in this case, the carbon does not have a negative charge, because we are using CCl4 molecule, we are not using carbene. In this particular reaction, no carbene is formed. No carbene is formed. Whereas in this reaction, obviously we can see carbene is being formed. So that is the difference. No carbene is being formed, so there is no negative charge on the carbon. So this hydrogen lost, we are getting it intact. Okay, this is not satisfying the carbon. So now the hydrogen from rearomatization, this will be taken up by this O minus. Remember, this hydrogen is from rearomatization, not from acidic hydrolysis. We have not done hydrolysis. We can get this product without any hydrolysis. So the product over here is this. And yes, we all know the name of this compound. This is a very popular compound known as salicylic acid. So this was salicylaldehyde because there was an aldehyde group over here, and this is salicylic acid because there's an acid group over here. Okay, so the differences we know between CCl4 and CHCl3. CCl4 versus CHCl3. Here carbene was formed. Here no carbene was formed. Here we got an acid. Here we got an aldehyde. Here hydrolysis was not needed because we use the H plus from rearomatization. Whereas in this case, hydrolysis was definitely needed because we did not get the H plus from rearomatization to satisfy the O minus. It satisfied the C minus. So in this case also salicylic acid is the major product, and the other product that we can get is this. So this part is benzoic acid. This is the OH group. At the para position, ortho meta para, ortho meta para. The para position, OH group is present. So this is para hydroxy benzoic acid because this is benzoic acid, hydroxy, para hydroxy benzoic acid. In this case also salicylic acid is a major product due to hydrogen bonding, and this is the minor product. So this concludes our topic on Reimer Tiemann reaction. We have done the reaction, the temperature, why 60 degrees Celsius temperature was required to convert so that the singlet carbene did not get converted into the triplet carbene. We have done the mechanism properly. We have done it with CCl4. CCl4 we have done. Okay, we have done the differences. So that covers pretty much everything about Reimer Tiemann reaction. So I hope you found this video helpful. I hope you like the mechanism behind it, how it behaved, how the OH minus behave both as a base and as a nucleophile. Thank you for watching. Definitely like this video and subscribe to my channel, and do turn on the notification bell because otherwise you would miss out on these videos. We are covering this phenol part right now. Okay? Thank you for watching. Goodbye.